Okay, hello everyone, and welcome to the online Spintronics seminar series, where you can listen to cutting-edge research talks on spintronics from the comfort of your home. I'm Kirill Belashenko from the University of Nebraska, and I will be your host today. For this 10th seminar of the series, Dr. Christina Psaroudaki will talk about her recent work on spin wave radiation by a topological charge dipole. Dr. Psaroudaki received her PhD in 2015 from the University of Crete in Greece, where she worked on low-dimensional quantum spin systems. She then held a postdoctoral position at the University of Basel in the group of Professor Daniel Loss, studying quantum and non-equilibrium dynamics of magnetic skyrmions. Then last year, she received a Marie Skłodowska-Curie Research Fellowship from the European Commission and is now a postdoctoral fellow at Caltech. Her research interests also include transport properties of frustrated magnets and quantum spin liquids. Please welcome Dr. Christina Psaroudaki.
Hello, thanks a lot for the introduction. So today I will be talking about my work on magnetic skyrmions and focusing on the most recent work related to spin wave radiation. So just briefly give some introduction on magnetic skyrmions. I guess most of you know that magnetic skyrmions are just the magnetization texture in a thin film, but is characterized by finite topological charge given by this formula here, where M stands for the magnetization field, and this is defined in a two-dimensional magnetic film. And this topological charge in principle counts how many times the magnetization wraps the unit sphere. These particles are related to very interesting topological phenomena, most notably the Skyrmion Hall effect that has been measured a couple of years ago in 2017 by two experimental groups, where the researchers were able to measure curve trajectories for the skyrmions in a direction perpendicular to the direction of the applied current. Of course, the earlier example is the topological Hall effect in the charge transport, and more recently, my collaborators from University of Basel demonstrated that topologically protected edge states, magnetic edge states, can exist in skyrmion lattices, ferromagnetic and antiferromagnetic skyrmion lattices. My work, however, focuses on individual skyrmions and their dynamics, such as the one that have been able to produce by locally injecting electrons from an STM tip, or for example, by converting a strip domain wall into individual skyrmions by passing it into a geometrical restriction. Of course, the skyrmions, individual skyrmions, have been in the focus of research due to possible applications. The most famous idea is when, for example, the magnetic skyrmion can play the role of an information carrier when it's encoded in magnetic nanowires. Okay, so the Skyrmion dynamics. The Skyrmion dynamics depends whether we want to study the skyrmion in a metal or in an insulator. I'm not sure if you can hear me. Can you hear me?
Yes.
Yes.
Sorry. Okay, sorry for that. So if we want to induce the translational motion and the dynamics of skyrmions in metals, the easiest way is by electric currents. And of course, in that case, the skyrmions exceeds high velocities, even more than 100 meters per second, when it's driven by magnetic pulses. However, in an insulator, there are several proposals how to induce the translational motion of skyrmions. You can do it either by magnon currents or using magnetic field gradients, or even thermal gradients, where you can move the skyrmions around using magnon currents. Now, from a theoretical point of view, how do we address the dynamics of such particles? So these usually are large particles, they are classical particles, and as any other particle, their dynamics is dictated by the Landau-Lifshitz-Gilbert equation, which is more or less the classical equations of motion, but with this additional phenomenological term that is introduced by Gilbert to account for damping in the system. The dynamics is a bit simplified if we just consider that the skyrmion is a particle. So it moves around, and in order to describe it, we need a few collective coordinates of position to study it. So this is the rigid assumption. And then we can derive an equation of motion for a particle, and this is known TLS equation of motion. So the first term here is the Magnus force. So it's a force that points out of plane and is proportional to the topological charge. And the next term is a damping term. So this accounts for interaction of skyrmion with the other degrees of freedom. However, those could be either electrons, magnons, or phonons, and we don't know the microscopic details of such a coupling. This equation is written only for the case of a magnetic insulator. Of course, additional spin torque terms should be added here if we study skyrmions in a metal. However, I will focus mostly on insulators. So what we did in an earlier work, we consider the case of the skyrmion propagation in a magnetic insulator at low enough temperatures, and therefore we just consider the skyrmion-magnon coupling. And what we demonstrated is that this coupling does not give rise to a dissipation term, a friction-like term. However, it gives rise to an effective mass. So the skyrmion, when it's coupled to magnons, behaves as a massive particle. Now, this is derived within a microscopic theory. I will skip the details, but since our derivation is microscopic, we are able to understand the mechanism of this mass generation. One of these mechanisms is spatial confinement. So if we confine the skyrmion spatially, then it will propagate as a massive particle owing to its confinement. And more recently, we also found that the skyrmion can couple to the curvature. So we can consider, for example, skyrmions stabilized in a curved environment, and this coupling to the underlying curvature is gonna give rise to effective massive terms. So just a few words on how we would derive and how we treat the system theoretically. In principle, we are able to derive, again, equations of motion for this collective coordinate of position. But now this collective coordinate is coupled to the magnon reservoir. And this interaction is given by response kernels of this form. So in principle, we are able to derive microscopically these dissipation kernels. As you can see here, this term contains memory effects because the skyrmion propagates, and as it propagates, it emits magnetic excitations, and at a later time, it reabsorbs it. But in most of the equilibrium cases, what we care about is what this term converts if we neglect this memory effect. So in principle, usually we look at the power law behavior. The most famous example is when we have an ohmic dissipation. So this exponent here is 1. That will give rise to a friction-like term in the equation of motion. However, what we found is that when the skyrmion is coupled to the magnon reservoir, the leading contribution is an omega squared term, and that will give rise exactly to this kinematic term, this inertia term. As an example that I will discuss our results, we consider the following free energy. So we have the exchange interaction here, and we take into account the Dialonczewski-Morilla interaction that, as we know, is in principle responsible for the interesting physics of skyrmions. And we also need either some anisotropy or a Zeeman term in order to energetically stabilize a skyrmion. So this is an example of the model I'm going to use to demonstrate some of our results. So this kind of model has a skyrmion lattice for specific parameters as a ground state. However, I will focus on the case of isolated skyrmions that exist above a ferromagnetic background. So I will be focusing only on isolated skyrmions. Now, on top of that, what we also care about is the magnetic excitations. Of course, we have the magnon continuum. So these are just traveling waves with the quadratic dispersion. However, below this magnon continuum, there could exist some localized deformations of the skyrmion, some bound states that correspond to these deformations with energy just below the magnon gap. And with this preparation, I would like now to address the following question. We know that we have a skyrmion in an insulator, and of course it's coupled to this magnon bath. What will happen if we turn on a driving field? So then we know that the field could exert a force on the skyrmion. However, the driving field could also act on the magnon reservoir. So if it's a magnetic field, it will couple to the spin degrees of freedom. Therefore, unavoidably, in most of the cases, it will couple to the magnon reservoir. And this magnon reservoir couples back to the skyrmion, giving rise to some additional dissipation. So I would like to explore this kind of terms that are usually neglected, and I would like to demonstrate that they could lead to some experimental observable quantities. So the setup we consider is the following. Imagine we have a skyrmion placed in a nanowire, and at some initial time, we turn on a time periodic magnetic field gradient, right? To make our consideration relevant, I would just like to point out that individual Skyrmion manipulation by local magnetic field gradients were recently demonstrated, right? So the authors were able to take a skyrmion, apply magnetic field gradient, and move it down here, and actually this process is reproducible. So they were able to even place it back. Now, second component that is relevant for our studies is the dynamics. So what happens when we turn on a microwave field? If the field is out of plane, then we know that the breathing mode will be activated. However, if it's in plane, then we will have a counterclockwise motion. So that like the skyrmion core is gonna circulate, is gonna perform this gyrotropic motion. So this has been either this has been also predicted theoretically and also experimentally observed in this skyrmion hosting insulator. For our studies, the magnetic field points out of plane, so the breathing mode is the mode that is mostly relevant. Okay, so let's go back to the setup. In principle, as I said, we are able to derive equations of motions that look like that. Now for this non-equilibrium situation, where we don't only drive the skyrmion, but we also drive the magnetic reservoir. Now this information is encoded in these magnon kernels. So this is just an external force, and this is a potential to take into account the repulsive from the boundaries of the nanowire. And the same way like we did before, let's assume that there is a time scale where the memory effects can be neglected. So I would like to simplify this dissipation term and try to derive more local terms. We demonstrate that this is possible. However, we can never get rid of the time dependence of the external drive. So we can derive terms that are friction-like or mass-like, or also normalization of the Magnus force. But in all cases, all these terms have a time periodicity that is inherited by the external drive. Of course, when we go to the limit of zero frequency, then only the mass term will survive. All the rest of the terms will vanish, as we expect. So the message here is that the skyrmion experiences a time-dependent dissipation, and that this is due to the fact that the magnon reservoir is driven. So if we like to study what is the result of this dissipation, So let's first see what is the solution of the equation of motion if we didn't have this type of dissipation. We only have the mass and the Magnus force, so the skyrmion starts from the center of the nanowire and will just perform this bounded periodic motion over time. I should also point out that the external drive is, the frequency is on resonance with the energy of the breathing mode in order to maximize the results of the drive. Nevertheless, if we take into account this additional time-dependent dissipation, the skyrmion is displaced. So the skyrmion is driven by the intrinsic magnons. It will perform a unidirectional helical propagation, and it will move along the long axis of the nanowire. So the arrow here shows the direction of motion. Okay, so I would like to stress out once more that there is no external force that actually drives the skyrmion along the long axis. It's just that through the drive, we change the way that the particle dissipates over a cycle of drive. So a quantity to study this kind of behavior, of course, we see, let's say, the motion of the particle in the short axis. It will just, is this yellow line, it will just oscillate. However, along the long axis, we see that indeed the skyrmion is displaced. So we can see this, this motion as an average over consecutive periods defined by this formula and plotted here by the blue line. So over consecutive periods of time, the skyrmion gradually starts to be displaced. And the same happens for the time derivative. Okay, so in the next project, we consider the case of the Brownian motion of the particle, because we know that in any physical realistic situation, there is always some thermal noise exerted on the skyrmion that will render its propagation stochastic. So we have this case where the skyrmion is coupled to the magnon reservoir. So what I have discussed so far is that we have an external drive coupling that drives the reservoir, and this reservoir couples to the skyrmion, gives rise to this driven dissipation. And now we also want to take into account the thermal noise, so these random fluctuating forces. In principle, we can rederive similar equations where now this random noise is this function psi. And we not only know this damping kernel, but we also know the correlation function of these functions. So we make two distinct approaches for this question. First, we ask what is the non-equilibrium stochastic dynamics, because in principle, we know that in equilibrium, for example, both of the dissipative term and the fluctuating term are related through the fluctuation dissipation theorem. And such a theorem is not expected to hold in a non-equilibrium situation. However, we were able to demonstrate that the fluctuation dissipation relation can be generalized as long as we have weakly driven reservoir for any arbitrary drive. These kind of considerations are a bit theoretical, so I will skip the discussion on the details because I would like to focus on a different aspect. I would like to focus on the quantum aspects of the stochastic dynamics. And when I say quantum, I mean, I would like to take this dissipation kernel and the fluctuating term and see what happens when we go to very low temperatures. So at zero temperature or just temperatures below the Magnon gap. So in an earlier publication, we know that the dissipative term, which is a mass term, has some temperature dependence. And if we go down to zero temperature, this term remains finite. So we have what we call a quantum mass, which is just a 0-point quantum fluctuations that do not freeze out even at vanishingly small temperatures. And the same thing can be also found for the stochastic dynamics. So now we can calculate the root mean square displacement, shown here. So here, sorry, so this is the mean square displacement, and here we plot the root mean square displacement, and we see, first of all, that it has some fast thermal activation, right? Because this is linear, therefore it's going to be quadratic, and it also remains finite even if we go down to 0 temperature. So these quantum terms, however, are plotted here as a function of the Skyrmion radius. So they are relevant only if we have very sufficiently small skyrmions, and at low temperatures, these terms are gonna be important. So just to make a comparison of why this prediction is sufficiently different from the classical case, the Brownian motion of the skyrmion has been extensively studied. However, within this phenomenological approach, and we also the assumption that the noise scales linearly with temperature, of course, and it's a white noise, so the different components are uncorrelated. So based on these assumptions, then one can make a very specific prediction that the mean square displacement will grow linearly with temperature. Right, so just to point out that our result is different. So we show that if we are able to access sufficiently low temperatures, then we're going to see not only a faster thermal activation, so different temperature behavior, but also we will see that even for very small temperatures, the mean square displacement remains finite. So this is just a suggestion how this quantum fluctuations could be relevant for the dynamics of skyrmion, and based on that we envisioned a different project, and that is considering the quantum depinning of a magnetic skyrmion. So in such a project, we consider that the skyrmion is pinned from, let's say, a local defect. So the skyrmion experiences this kind of potential. And we also apply a linear force that is going to tilt the potential and kind of reduce the tunneling barrier. In principle, the skyrmion at enough temperatures can escape by thermal activation. However, there's always the case of quantum tunneling. This has been experimentally observed in singular mesoscopic particles, for example, a domain wall or a vortex in a superconductor or a magnetic vortex. In all of these cases, or at least in most of these cases, this kind of phenomena is dominated by inertia effects. However, we point out that in a skyrmion, inertia effects actually is not so relevant. So the whole dynamics is dominated by the topological charge, by the topology of the problem. So to make such observations experimentally relevant, we need to have two cases. The first of all is that the decay rate, so the time that we need to wait until the tunneling processes happen is not very large. Of course, if we wait for sufficiently time, let's say infinite time, the tunneling process might be possible. However, we just want this inverse time to be within a few hours, let's say a few seconds or a few hours. So the second thing we need to require is that the crossover temperature, so the temperature at which the thermal activation dominates, is not very, very small. It needs to be also experimentally accessible. Okay, to make a long story short, what we predict is for sufficiently small skyrmions that are within, let's say, a radius of a few lattice-sides, 10 lattice-sides, in the experimentally accessible temperature of 100 millikelvin, such processes could happen within, let's say, some seconds. Okay, so that brings me to the last part of my talk, which is a most recent work. So far, I have been describing the dynamics of skyrmions, but I didn't really specify a specific model. So in principle, I use the model to apply my results, but these results could be easily extended for different structures, for different magnetization textures as long as they are topologically particles. In principle, the Skyrmion family is broader. So depending on the Dialonczewski-Morilla interaction and depending on the material, this Dialonczewski-Morilla interaction is dictated by this, the crystal symmetry of the material. And for example, it will have a different form and different orientation if we have cubic interfacial C2V or a D2D symmetry. And depending on the symmetry, then we will have a different magnetization texture. For example, we know that a non-symmetric material, we have cubic symmetry, and that will stabilize the Skyrmion block. However, if we have interfacial DMI, it will stabilize the Skyrmion nail. And different textures have been predicted and also experimentally observed. And these textures, depending on the crystal symmetry, they have an opposite topological charge. So if these here are defined by topological charge -1, these are antiskyrmions and they have an opposite topological charge. So how skyrmions and antiskyrmions differ, besides that they have the opposite topological charge? Of course, they will be deflected in opposite directions with respect to the Skyrmion Hall effect. So the Skyrmion will go in this direction wherever they, however, the antiskyrmion with an opposite topological charge will be deflected in an opposite direction. And it has been suggested that if they are realized in bilayers, with some spatial in between the two layers, the coupling of a skyrmion and an antiskyrmion will result a bound state with a vanishing topological charge, and therefore there is no Skyrmion Hall effect. It's just the bound state will propagate without any deflection. What we also observed, that something that distinguishes a skyrmion from an antiskyrmion is how this mode, how this clockwise mode happens for a skyrmion or an antiskyrmion. So imagine we have a skyrmion and an antiskyrmion with the same size. So the skyrmion, if we excite it by in-plane magnetic field, it will perform a counterclockwise mode, something that, as I said before, has been experimentally verified for this material. At the same energy, for an antiskyrmion of the same size will perform a clockwise rotation, right? So we have two textures that actually rotate in an opposite way. This is an observation that we made by diagonalizing the Magnum Hamiltonian for either a skyrmion or an antiskyrmion. And what we found is that the Magnum energy, the energies do not depend on the topological charge or the helicity of the textures. However, the corresponding deformations depend on the sign of the topological charge. So for example, a skyrmion that performs, as I said before, a counterclockwise, this eigenstate will correspond to deformation in the opposite direction, gyrotropic direction, for an antiskyrmion. So an antiskyrmion will perform a clockwise rotation. So on top of that, we also found a breathing mode and an elliptical deformation. And here are the energies for the Magnum. Scattering states were just, the normal spin waves that exist above a gap, and they have a quadratic dispersion. So then we ask the following question. Since we have like two topological charges that rotate, they perform gyrotropic motions in opposite directions, is it able to have a spin wave dipole radiation? Somehow sometimes being inspired by the charge dipole radiation. And in order to answer that, we envisioned the following setup that consists a topological charge dipole. So we have two layers, and the upper one hosts a skyrmion and the lower one hosts an antiskyrmion. And we allow for an interlayer coupling. So we allow for these two layers to interact. And we also turn on an AC magnetic field in plane that will activate the gyrotropic motion of the skyrmion and the antiskyrmion. Okay, so then we would like to address the dynamics of it, just a very fast summary of how we're going to solve the problem. So we would like to find the dynamics of the magnetization. Therefore, we need to solve the LOG equation now using micromagnetic calculations. In each layer, as I said before, we have a Hamiltonian like that. So the exchange interaction, the Dialonczewski-Moriya, that now could take different forms, and also an out-of-plane Zeeman term. We also take into account the interaction of the two layers and an in-plane oscillating magnetic field. Now, the frequency of this field is usually most of the results I will present shortly is under the resonant condition. So the external frequency matches the frequency of the clockwise or counterclockwise motion of the skyrmion, which is approximately at the magnetic field that we have to apply to stabilize the skyrmion. If we now see the dynamics of a single layer, so when the interlayer coupling is 0, and then what we see is that the spin wave is emitted in a radially symmetric direction. So the spin waves here are defined as fluctuations over the oscillating ferromagnetic background of the Z component, and each of the texture represents just an oscillating monopole that emits radially symmetric waves. To study now the bilayer, we focus on two important quantities. The first one is the collective coordinate of position. So we'd like to associate what are the characteristics of the emitted spin waves with respect to what is the path that the skyrmion performs. So therefore, we define the collective coordinate of position, and we also care about the charge separation distance, so the distance between the two charges. And on top of that, we also observe that the fluctuations of the upper layer, if we have particles that have the same charge, are equal to the fluctuations of the lower layer, or if we have opposite charge, they are connected to the symmetry. So in all cases, I will present results for the upper layer. However, we talk about the collective modes of the bilayer. Okay, so now we kind of thought to take into consideration different cases. Either we have two layers with opposite charge, two layers with the same charge and the same helicity, and two layers with the same topological charge, but now we have different helicity. And what we found out that is in each of those different cases, the characteristics of the emitted spin waves are linked to the topology of the source. So we have either directional spin waves, uniformly symmetric spin waves, or spin waves with a spiral structure. And I would like to focus in each of those different types. So if we focus on the first type, where we have two layers with opposite topological charge, that is going to form a topological charge dipole. So both the skyrmion and the antiskyrmion perform these elliptical paths with opposite sense of gyration. And the charge separation is going to perform an oscillating motion along this axis. Now we see the emitted spin waves. The emitted spin waves, they have a preferred direction, and this preferred direction coincides with the direction of the topological charge separation, meaning that it's meaning that it's the interacting topological charge that is the source of these spin waves. And this is further supported if we look at the radiation pattern, which is just the Fourier transform of the spin waves, the spin wave amplitude, averaged over one period of the drive. And as we clearly see, it has the characteristic dipole, two-source dipole feature. Just some note here. that although I saw results for the upper layer, right? So the lower layer is connected through this relation. So if the upper layer emits, let's say, in this direction, the lower is going to emit in the opposite direction. Okay, so then we thought to consider different combinations of helicity just to see how the results are going to change. So in the first case, we consider a Skyrmion Bloch and a Skyrmion Nell. Then if we change the relative helicities, so if we consider a Skyrmion Nell and an anti-Skyrmion Bloch, then we see that the charge separation performs a motion along a different axis. And also the radiated spin waves are also emitted in these different axes. Therefore, the relative helicity can be used as a way to control the direction of the emitted spin waves. Now we turn our attention to the second type, where we have the same topological charge and the same helicity. This is probably the most boring case because we have two identical particles performing the same kind of motion, and the emitted spin waves are radially symmetric, as we would expect for a monopole. So now we would like to see what are the distinct signature of the interaction of the two charges in the radiation field. Therefore, we consider to study the far field amplitude within an annulus centered around the skyrmion. And we report this value as a function of the interlayer coupling. So in the first case where we have a dipole, this amplitude grows linearly, almost linearly with the interlayer coupling. Also further supporting our interpretation that the source of the directional spin waves is an interacting topological charge dipole. In the other case of the second type, where we have a monopole, although the two layers interact, the emitted spin waves are not affected by this interaction. So it has a very weak dependence on the exchange, on the interlayer coupling. Another further way to manipulate the amplitude of the spin waves is by changing the ratio of D over J. So if we decrease the ratio of D over J, the Dionzinski-Mourier interaction over the exchange interaction, what we observe is that the amplitude, of course, grows. So the system becomes less rigid and the amplitude grows. And it grows with a scaling J over D squared. And of course, this is just the amplitude with respect to how close we are to the skyrmion. So if we go further and further away, because we have a finite damping, then the whole amplitude should die. Just to have an estimation in real units, for example, when we excite a skyrmion of radius around 44 nanometers with some, let's say 57 gigahertz, then the emitted spin waves will have a wavelength of around 42 nanometers. So it's the nano size of the skyrmion ensures that the emitted spin waves are also have a very short, relatively short wavelength. And that brings me to the last type that we consider when we have two particles with the same topological charge but opposite different helicity. And if we consider the case of a skyrmion, so here we have a Nell skyrmion. So this is the blue path, and a Bloch skyrmion was going to perform a smaller path. Therefore, the charge separation distance is going to perform a rather circular path, and the emitted spin waves are going to have a spiral structure. And then if we have an opposite topological charge, so the whole all the particles now rotate in opposite direction, and then the emitted spin waves will have an antispiral structure. Okay, so one last point would be just to characterize those modes with respect to their dispersion. And we do that by focusing on the radiation pattern. So here we plot the radiation pattern for all the three types and for two different frequencies. Now we're going to vary the external frequency and see the response of those modes. Now if we are on resonance, we first notice that there is a short wavelength mode, what we call a resonant mode, with relatively high intensity. However, if we just slightly increase the external frequency, the intensity of this mode vanishes. So here we plot the intensity of this mode as a function of the external frequency, and what we observe is that it has maximum close to the resonance condition, and it vanishes for higher frequencies. So this is the resonant mode that I presented so far. It's a mode that is emitted from the interacting topological charges and has characteristics that are linked to the topology. On top of this mode, we also find a long wavelength mode. It's depicted here by this yellow circle. These are the usual magnons. So then we record the wave vector of these usual magnons with respect to the external frequency, and we found that they have the expected quadratic relation. So on top of the usual bulk modes, we also find, I would like to emphasize that we also find this resonant mode that exists only when the frequency is very close to the resonance condition. Both of those phenomena can be visualized in this video. So you can see here is the location of the resonant mode, but as we increase the frequency, the intensity drops. And here we see the bulk magnons that as we increase the frequency, they dominate over the other mode. Now, this kind of modes, directional and spiral spin waves have been observed in other systems. For example, spin torque nano-oscillators can be used to show that we can induce directional spin waves. For example, in this theoretical paper, the author suggested that if we place two spin torque nano-oscillators in two or more, we can have directional spin waves as a result of interference. We can also have spiral spin waves in spin Hall nano-oscillators where the gyrotropic motion of a dynamical skyrmion emits spiral spin waves, and of course something that is more relevant to our consideration, a stack of vortices will emit spiral spin waves when they are externally excited. However, we showed that we have a more broader different types of spin excitations depending on the topology of the source that can be manipulated in various ways. So I'd like now to summarize just the part that has to do more on how we can manipulate Skyrmion dynamics using AC fields. One part had to do with this unidirectional propagation that we can induce. And the later part had to do with a spin wave radiation by topological charged dipole and a very broad family of spin waves that we could excite that have different characteristics, but in all cases they are related to the topology of the charge. So most of this work has been done when I was in the group of Daniel Loos, and this last part has been done in collaboration with Sebastian Diaz and Tomoki. And this is a photo of us in a very, very warm day in Basel. So thank you for your attention.
Thank you very much, Christina, for this interesting talk. So we can now take questions. If you have a question, please use the raise hand feature in Zoom under participants. And please keep your camera off and sound muted until I call upon you. Oleg Chernyshov, please go ahead.
Yeah, perhaps not directly related to the Skyrmion wave emission. There's in fact an exact duality for vortices. If you have vortices in an easy plane ferromagnet, then you can show that they behave exactly like electric charges. The electric charge is equal to the vortex number, and spin waves become essentially become photons. And so there, the rotation of vortices is precisely mapped onto the radiation of photons by a rotating charge.
You mean the dispersion?
Not the dispersion. The very process is basically a one-to-one correspondence. So if you have an easy plane ferromagnet, then you have magnons with a linear dispersion, which is exactly like photons. And then vortices become charged particles, and so their rotation certainly creates photons.
Mm-hmm. Yeah, probably one can demonstrate that for skyrmions as well. However, I'm not sure, is this resonant mode that I have been talking about? It's probably more the bulk magnons that are affected by the two vortex interaction.
All right, thank you.
Thank you.
Okay, thank you. Sucheta, the next question, please.
Yeah, hi Christina, that was a very nice talk. So my question is regarding the coexistence of skyrmion and antiskyrmion. According to you, what can be the criteria of this kind of topological charges to coexist in a like lattice or a single layer? Or why they do not show always the coexistence in many cases?
We did not consider the coexistence of the same material. What we thought of is, we know we can have different materials that support either skyrmions or antiskyrmions. And then you create bilayers of those materials. So we place the one material under the other, and in principle, you can put a spacer in between to control the interaction of those two. There are other, of course, models, as you said, that for example, if you don't have the Antiskimaria interaction, if you have frustrated interactions, you can stabilize in the same model, the same material, skyrmions and antiskyrmions, but that's not what we considered here.
Okay, and another question is when you talk about the spin wave radiation from this kind of topological charges, do you consider the damping of the intrinsic damping of the material or the system, or there is some kind of dephasing within the mode, or that vary? I mean, that can vary with the damping or something.
So here we considered. So that's a question for the last part, right?
Yes, I mean, the damping is the constant damping. I mean, the damping of the individual modes are constant, or they are the intrinsic damping, or they face some dephasing with one another.
No, we do not consider such processes, although they might be relevant in these emission processes, but we just consider a constant damping within this Landau-Lifshitz-Gilbert approach that takes into consideration the damping of the spin waves.
Okay. Thank you so much.
Thank you. Hilary Meyer-Hurst, next question, please.
Hi, Christina. Thanks for a nice talk. I might have missed it, but what are you assuming about the coupling between layers? Do you need to have a weak or strong coupling?
Well, it's weaker than the exchange coupling of each layer, right? Oh, sorry. Yeah, okay, try that. So this is like a summary of the interaction. I don't know if you can see that. So the J interacting is just a ferromagnetic interaction. It's smaller than the exchange coupling. So it takes values, let's say, from 0 up to 0.3.
Okay, thank you.
Respect to J. Yeah.
Okay, Shen-Fan has a question, please.
Thank you, Christina, for the nice talk. As an experimentalist, every time I see talks like this, the first thing came into my mind is can I use this in future, let's say, data processing, data transmission applications, or even neuromorphic computing? So the question I have is regarding to your last part. When you have two topological charges that can precessing that can generate spiral spin waves, how fast does it decay? I know there's going to be exponential decay due to the damping, But is this also like similar to the radiation of the oscillating dipoles? It decays with this additional 1 over r decay or 1 over r squared decay. And also, can you comment on if these spin waves can further manipulate second skyrmions, neighboring skyrmions?
Sorry, if they can manipulate?
If the spin waves can be generated from one pair of skyrmions, is it easy to manipulate a second pair of skyrmions just a couple of nanometers, couple of tens of nanometers away?
So you mean you generate the spin waves and then they interact with another?
Right.
Yeah, I mean, of course. Yeah, of course, one can envision different, ways to make use of these emitted spin waves, and one would be to actually make these emitted spin waves couple back to another pair of skyrmions. Now with the decay, we have in most of the results I presented here, for example, here, we see this decay with respect to the distance, right? So how far we go from the skyrmion core, which is the emitter. In this case, however, we have a very strong Galen-Zieske-Mourier interaction. So we have almost to be equal to the exchange interaction. If we make this assumption a bit looser, of course, the whole amplitude grows, and of course, it dies not as fast. But I don't think the way it dies is gonna have a different scaling.
Oh, okay, thank you.
Okay, I think there are no more questions. Let me ask a quick one. Have you estimated, maybe it said that the radiated power in some terms that can be compared with typical spin currents and devices?
What we calculate is the magnetization amplitude, right? We haven't calculated the power, but that is something that we could do, yeah.
Okay.
You mean whether it's going to have these dipole-like features? Or?
Well, I mean, like Professor Fan just implied, it would be interesting to use these, the flux of these spin waves to manipulate something. And then we kind of know the typical fluxes that are needed to manipulate magnetization in nanostructures. Usually think in terms of spin currents or charge currents. You can imagine, spin waves carry angular momentum, so you can probably find an equivalent value to describe the intensity of this radiation. Okay, it looks like we don't have any more questions. So thank you very much, Christina, for this nice talk.
Thanks a lot.